Subscribe to this channel and press the bell icon for more updates.
So far we have discussed that particles having periodic motion and satisfying the condition of acceleration proportional to displacement and acceleration and displacement being oppositely directed will execute SHM. We have also discussed examples of SHM like simple pendulum, like motion of a liquid in a U-tube, and there can be many more. We have also discussed that during the SHM, the total energy remains conserved, that is the kinetic energy plus the potential energy remains constant. We have obtained a relation for the time period of the particle executing SHM. Today, we shall apply this knowledge for understanding waves. These waves are formed by the vibration of the particles of the medium and are also termed as mechanical waves. Somewhere they are also known as sound waves, but we shall have discussion about them more. Let us imagine that the medium has particles. The medium could be solid, liquid or gas, but the particles of the medium, let us say, are regularly arranged like in a line. Like I have shown about 10 and 11 particles. And if we start or initiate the first particle to execute SHM, there are again two ways for this particle to execute SHM, either along this or in a perpendicular direction. Let me just consider this mode of vibration of the first particle executing SHM. This particle at number 1 executes SHM along this, and it is important to understand, as this particle starts executing SHM or starts even moving, the second particle gets induction from the motion of the first particle and also will start moving. From the motion of the second particle, the third particle will also have the induction process and will also start moving. Likewise, I would say that the vibrations from particle 1 are passed on to 2, to 3, to 4 and so on. In other words, the vibrations are passed on from particle to particle absolutely like this, that if I give the book to the first student without actually leaving his place just passes it on to the next neighboring student. The next neighboring student passes it on to the next neighboring student, and finally the book is passed on even to the last student. So absolutely on the same pattern, the vibrations starting from the first particle are passed on to the second, third, fourth and so on. You can further see that if I divide the entire motion of the first particle in 8 parts like this, you can see the entire vibration of the first particle is being covered in 8 parts, of course in time capital T, the time period of the motion of the SHM. As it moves from the initial position to 1, as shown here. Let me say the second particle starts its motion, and as this particle moves from 1 to 2, this particle moves from 0 to 1. And as this particle moves from 2 to 3, this moves from 1 to 2, and this third particle moves to 1. Then as it moves from 3 to 4, this will move from 2 to 3, this will move from 1 to 2, and this will move to 1. This process goes on. Now let us see what really is happening. And if you understand this component, you will seriously be able to understand what is the meaning of wave. See, this particle is not leaving its place. This particle, or in fact, no particle is leaving its place. This particle is executing SHM about its own position. Same way, the second particle is executing SHM about its own position. Third particle, fourth particle, and all particles will finally be vibrating and executing SHM at their own positions without actually leaving the positions. And in the bargain, they are transferring by a process of induction the vibration to the next neighboring particle. However, one more thing let's see. As this particle starts and moves to position number from 0 to 1. As it moves to 1 and 2 starts. So don't you see that between particle here and here there is a difference. The difference is this is already moved, it is advanced, and this has just to start, and this is not even starting. So there is a gap, time gap of starting the motion between particle 1 and 2. Likewise, there is a time gap between the particle 2 and 3. So the second property which we understand, that there is a time difference between any two particles. Look, when this third particle at position 2, the fourth particle is at position 1, the fifth particle is about to start. Likewise, see, this total time of vibration is capital T. In this 8 parts, we have divided the time as T by 8. So therefore, the second particle is behind the first particle in this time, by this time. Similarly, the third particle will always be behind the second particle by the same time. So therefore, we'll say there is a constant time difference between the vibration of any two consecutive particles, or we may as well say constant phase difference between any two consecutive particles. This is property number 2. Remember, the first property I said, no particle is leaving its place and they are vibrating about their initial positions, mean positions. Second property, there is a time difference, or precisely what is known as the phase difference in the vibration of any two consecutive particles, and that phase difference is constant. Now third, this particle has this as the amplitude. The second particle will have exactly the same amplitude. The third particle will have exactly the same amplitude, and so on. So the third property is all particles are vibrating with the same amplitude. Third, all particles will vibrate with same amplitude. So three properties. And now let's see what has actually happened. The process of vibration initiated by the first particle has been induced in second, third, fourth, and finally with all particles of the medium, where finally we find that every particle vibrates at its mean position with same amplitude but with a constant phase difference between any two consecutive particles. Now, whereas this is happening, so what can we now imagine? We can imagine that if you can freeze the motion of all particles at any given point of time, then you will see as this particle has completed its vibration and has come back here, this particle is behind and is at the position 7. This particle is behind this and at the position 6. So now see. This particle has completed the vibration and is at this position. This particle is behind this and is at 7th position. This particle is still behind it and is at 6th position, 7th position, 6th position. This particle is behind this and is at 5th position. This particle is behind and is at 4th position. This particle is behind and is at 3rd position. This particle is behind and has 2nd position. This particle is behind at 1st position, and this particle has yet to start. Let me put it as 0. Can you see, starting from 8, 7, 6, 5, 4, 3, 2, 1 and 0, these are the positions during the motion of these particles. If I theoretically imagine a line joining the positions of various particles, it will be like this. See, these are the positions of the various particles being joined by a line. Does it look like a wave? Yes. So a wave is what then? A wave is the location, is the locus of various particles vibrating at any given instant of time. Now further, and a very important point. After this, when it has completed one wave, when 8 particles will now move on to 1, the 7 will move on to 8, the 6 will move on to 7, let me cross it, this will move on to 6, you see this 7, and this will move on to 8, this will move on to 6, and this will move on to 4, this is 7, this is 8, and this is 7, and this is, so like that, you know, the so it is moving as if it is shifting. This is the first wave, and this is next. The vibrations have transferred to the next particle. So this is the wave after one completion, one round. Now, as if you know, the wave, instead of starting from A, the wave starts from B. You can see, if you just imagine, the wave seems to have started from B. Can we say that the wave has shifted from this A to B. So constantly the wave is shifting, and this is the direction of motion, propagation of wave. Now, I hope you will recall all particles started their vibrations about their mean positions only, with the same amplitude but with a constant phase difference. And now we find the definition of a wave is just the, if the location of various, the positions of various particles is joined by a line, it gives like a wave-like picture, and the wave itself shifts in the direction of propagation. Now how much is the shift? As is this. If this is T by 8, so this shift is also T by 8. So the wave shifts in the direction of propagation by the same amount as we are considering. We have divided the entire vibration in 8 parts, so it will be shifting by 1/8 of the total time period. So now let's see more properties about this wave. The wave, again I would like to emphasize, wave itself is just a symbolic picture of the location of various particles vibrating at any given point of time. If it is joined by a line, it gives a wave-like shape, wave-like picture, which shifts in the direction of propagation. Now let's see about the particles once again. This is, since each particle is going to vibrate with the same amplitude, therefore there is a uniform stress in the medium. If some particle understands that it is not going to vibrate, well, obviously there will be more stress at that point. Since all particles have to vibrate and they have to vibrate with the same amplitude, therefore the stress is uniform. The density also is uniform because the particles are at their own positions only. They haven't moved at all except vibrating at their own mean positions. So therefore uniform density remains in the medium. The uniform stress between the particles remain in the medium, and hence these are the 5 properties of the particles vibrating in the medium. 1. Each particle vibrates with the same amplitude about their mean positions. They don't leave their positions, and except that there is a constant phase difference between the any 2 consecutive particles, rest, the stress and the density of the medium remain same. A wave is defined as the locus of positions of various vibrating particles in the medium. Next, the shifting of wave-like picture. What is shifting? Only the wave-like picture is shifting. Particles are not shifting. And in this bargain, you see the wave-like picture shifts in the direction of propagation, and this is what I have shown. So these are the different properties of the for what is known as a progressive wave. Just one more point. See what we have defined. This as a wave. This distance we would like to call it as wavelength. In how much time has this been propagation been achieved? In time capital T. As this particle about its mean position completed one vibration in time capital T, and the vibrations have been transferred from this point to this point over a length lambda in time t. Therefore, we define velocity of more propagation. V is equal to distance upon time, V is equal to lambda upon t, and 1 upon t is known as frequency of motion of the particle, and therefore V is equal to 1 upon t lambda or nu lambda. Now there is one very important part I would like to say. This V is what? Is it the velocity of the motion of the particle? No. It is the velocity with which the vibrations are being transferred in the medium, and therefore the velocity of wave. Velocity of the motion of the particle we will be discussing later. So with today's discussion of starting a wave, which is nothing but transference of vibrations from particle to particle, and it transfers the vibration to a length of lambda during the time capital T, giving us the wave velocity as lambda by t or as nu lambda. With this discussion, I will take this topic further in a practical word, where you will appreciate that how does these waves influence in our day-to-day life. Thank you.